5.4 part 2. Now we're going to get into a little bit more in-depth scenarios of what happens if we run out of electrons to use. Before we do that, kind of like we did in the last one, if you see 2 dashes or lines, that is a double bond. You probably figured that out already. Okay, but just want to kind of make sure we're all on the same page. So how many electrons are being shared, do you think, between the carbons? Again, making sure you're answering the question that's asked. It says electrons, so there are 4 electrons. How many electron pairs? There would be 2. Okay, let's jump down here. So if we have 3 dash lines, then as you guessed, it's a triple bond. So again, being able to answer the question that's asked, and this is where what might trip you up on your summary quiz or quarter test or the Regents exam. Number of electrons being shared is 6, and the number of electron pairs would be 3. Now I understand that this isn't super clear, but that is a triple bond between those 2 carbons. So just be on the lookout for it. It'll always be clear. All right, so what happens now? This is kind of step 5B in our process. So step 1 and 2, we're figuring out valence electrons. Step 3 was your skeleton structure, connecting with single bonds. Remember, you always start with single bonds. Then step 4 was lone pairs, and then making sure everything had 8. Well, what if you have too many electrons that have been used, and then we have to subtract 2 unshared pairs, changing it to a shared pair until the total number of electrons is correct. So basically what this is implying is what happens if one of your atoms doesn't have 8 electrons, doesn't have a full octet. Then you have to start forming double bonds. So let's jump into a couple examples together. So process is still the same. Figure out your valence electrons. So I've got carbon. I've got 1 carbon. Carbon has 4 valence electrons. I've got 2 hydrogens. Again, each has 1. And then I have 1 oxygen, which has 6. So 4 plus 2 plus 6, I've got 12 valence electrons. Nothing new here. Now, draw your skeleton. Well, carbon, if I see carbon, I know it's going to be my central atom. I've got 1 hydrogen, I've got 2 hydrogens, and I've got an oxygen. Okay, so I'm going to connect them with single bonds. Subtract out, there's 6, so I've got 6 more lone pairs. Well, who is going to get the lone pairs? Hydrogens are good, so I'm going to go with oxygen, right? Oxygen, how many more does oxygen need? It needs 6. Oh, good, I have 6 left over, so minus 6, boom, I've used all my valence electrons. So I'm good, right? Well, remember, our last step is to make sure that every atom is satisfied. Hydrogens are good, they each have 2. Oxygen has 2 in the bond. It's got 4, 6, 8. But how many does carbon have? So again, when you get done with these problems, you've got to ask yourself, does every atom have 8 electrons? Carbon needs how many? Carbon needs 2 more. However, can I just put a lone pair there? Absolutely not, because I've run out of electrons. Okay, I don't have any more electrons to give, so now I have to use a lone pair. So notice how I have all these electrons here on oxygen. Okay, so what's going to happen to get 8, I'm just going to erase this just to have some space. To get to 8, and again, the reason why this happens is because of energy, okay? Oxygen, it's stable, right? It's stable with 8, but carbon doesn't have it. So there's a lot of strain on this molecule. Oxygen is willing to share an entire pair of electrons so that carbon can have 8. I'm sorry, I drew that arrow incorrectly. So it's going to form a double bond. So what's going to happen is our structure now is going to look like this. Okay, hydrogens are the same, and there's going to be a double bond between oxygen and carbon. So now if we take a look, right, I've got 2, so hydrogen's good, hydrogen's good. Now that's 2, 4 on carbon, 6, 8. Carbon's happy because it's now got 8 bonds. I'm sorry, 4 bonds, 8 electrons. Oops. And now count up oxygen. Oxygen has 2, 4, so 2, 4, 6, 8. All right, it's happy. One thing to note, guys, over here, double and especially triple bonds are a last resort. Okay, it's a last resort. You don't want to just start going double bond and triple bond happy, because think about it. What are electrons? Electrons are negative. So right here in this double bond, you have a lot of negative charges, okay? You've got a lot of negative charges right here. That takes a lot of energy to keep them together. They would much rather be in single bonds if possible, okay? But if we run out of electrons, then we have to form double bonds. All right, let's take a look here at carbon dioxide. So this formula, you guys should know the formula of carbon dioxide, even though we haven't done naming yet. We got CO2. So go ahead, count up your electrons. I've got 1 carbon, I've got 4 valence electrons, plus I've got 2 oxygens that each have 6. I know that doesn't look great over there. Give me a second. So 4, I've got 1, okay? So 4 plus 12, I've got 16 electrons that I need to work with here. So again, start the same way. I've got carbon, oxygen. I'm going to connect those, so now I'm going to subtract out 4. We've got 12 more. Well, each oxygen needs 6 more, so there's 12. All right, now I've run out. My oxygens are happy, but they're carbon. No, carbon is not happy. There's only 4. So this needs to have a lone pair from this guy. It needs to have 4 more electrons. So let me ask you this. Would this guy want to do this? Now don't draw this down. Just watch and see what I'm going to do. So I've got 2 options of where I could get these electrons from. I could form a double bond, a triple bond, or what I could have done was I could have taken 1 pair from one oxygen and 1 from the other. Which do you think is more likely to happen? Now, the answer is the 2 double bonds, okay? And why do you think that might be the case? Well, the answer is energy, guys. There's a lot less energy in 2 double bonds for a molecule than there is a triple bond, okay? So carbon dioxide will actually have 2 double bonds. And what we're going to start to see, and this is kind of getting into the next video a little bit, the structures are going to start to become more spread out. Okay, because again, negative electrons here, negative charges here. The like charges repel one another, so they will start to spread out. Now, I know I may have just lost some of you guys with that, and that's okay. Ask questions where you need the help. I want you guys to go ahead and try doing HCN. All right, so we've got 1 times 1 plus 1 times 4. You probably guys can start doing this part in your head. You probably don't have to write that out. So we have a total of 10 valence electrons that we have to use. Will hydrogen be my central atom? No, it can never be the central atom. So I'm going to go to the next one, which is carbon. So I've got carbon, I've got nitrogen, I've got hydrogen. We connect them with bonds. So there's 4 electrons. So I've got 6 more. Nitrogen needs 6 more. Boom. All my electrons are gone. Is carbon happy? No. Now, is there a multiple place where you can take electrons here to form multiple bonds? No, there's only nitrogen, right? Hydrogen cannot form multiple bonds, and it doesn't have any lone pairs to use that. So we're going to take 2 lone pairs here to form a triple bond. Now you might be asking yourself, well, how did we do a triple bond here? Because there's a lot of energy. Guys, we only had the choice to make a triple bond here. We didn't have the chance to make 2 double bonds. So when in doubt, this is why triple bonds are very, very last resort. It has to be the right condition for it. All right, so same idea in those problems. Now we're going to talk about these things called polyatomic ions, okay? So we'll talk more about those in the next unit. You'll have to memorize some, so be aware of that. This is one additional step, and it's when we're counting valence electrons, we have to include the charge. So must include the charge when we count it. If it's a positive charge, we subtract that number from electrons. If it's negative, we add it to the number of electrons. Make sure that you put brackets with a charge around your final structure. Much like what we did with the ionic bonding, same idea. So, same process, guys. The only difference here is the initial counting piece. So let's jump right in. I've got 1 nitrogen. Nitrogen has 5 valence electrons. I've got 3 oxygens. They each have 6. Now, notice I also have a charge. if we were to just add this up, okay, 3 times 6 is 18, plus 5 is 23. Is it possible, do you think, to have an odd number of electrons in a structure? No, it's not possible. Why? Because they're lone pairs of electrons. They're bonded pairs of electrons. Everything happens in pairs with electrons. So if you have an odd number, something's wrong. Look for a charge or redo your math. Now this is negative. Am I going to subtract one or am I going to add an electron? Negative, I add because I'm gaining electrons. So we have a total of 24 electrons that we have to use. That's the only new piece here. The other part of making sure we have brackets and a charge comes at the end. The rest of the process is the same. So my central atom is nitrogen. We've got 3 oxygens all around. Start with single bonds first. So I'm going to subtract out, 6. Now I've got 18 more. Sorry about that. Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so there's 18. Oh boy, oxygens are all happy. Is nitrogen. Does nitrogen have 8? No, it does not. Now, the piece here, you could take a lone pair, guys, from any of these oxygens. It does not matter which one you take it from. Okay, so I'm just going to show you that arrow, but I'm going to just redraw it. So I have something that looks like this. My final structure is going to have brackets with a negative charge on it. If you don't put the brackets, it's okay. If you don't put the charge, it's wrong. You have to make sure that you have the charge or else it is incorrect. Okay? And then the last step, make sure that everything has 8. Each oxygen has 8. And then nitrogen does as well. Now, you could have also had this structure. So I'm going to draw something down here that I encourage you guys to draw as well. We could have had a double bond over here. Okay. Could have been that. Or it could have also been this. We could have taken it from the bottom oxygen. So we could have had something like this. Guys, this is called resonance. Okay, this is an AP concept. We will talk about it throughout the year a little bit. But resonance just means that you can have multiple structures, multiple locations of electrons simultaneously. So all 3 of these structures are actually occurring at the same time. All right, those electrons are constantly moving. So resonance. Be on the lookout. That could be a prize question or a bonus question. Just throwing it out there. All right, you guys pause the video and try sulfate on your own. All right, so here we go. I've got, excuse me, 6 electrons from sulfur. I've got 24 from oxygen. And then this is from my charge. Okay, so this is from oxygen. This is from sulfur. And then the last one is charged. So I have a total of 32 electrons. So here we go. Sulfur, 4 oxygens, single bonds first. Minus 8, I've got 24. Oh, look, it's going to work out perfectly. There is no double bond or triple bond needed in sulfate here. Brackets, my charge is a -2. All right, I'm sure you probably have questions, especially as you take time to do practice. Call me over, ask questions as you need, and I'll see you in the next video.